Well, let's get started. It's like I have a lab meeting at 11, and so then if this, I'll send Dr. Minima. Okay, if this goes well, then we can do this again next Friday. So let's see how far we can get through this. So I want to talk about symmetry breaking. And spontaneous, specifically spontaneous symmetry breaking, okay, and Goldstone's theorem. I'm not going to get to Goldstone's theorem today, but I hope to get to a point where I'll be able to say this example generalizes to Goldstone's theorem. So first, let's start off with point particle mechanics. So you have a Lagrangian, and it's going to be a unit mass, and so I'm going to use Q for the coordinates. And again, so basically taking m is equal to 1. The dot means time derivative. So this is the kinetic energy term. And it's going to be an anharmonic oscillator. Right? So there's your standard harmonic oscillator or spring term. And then I'm going to add in a term like this. And this is the anharmonic term. Okay, and so what are the equations of motion for this? Okay, so you, again, this is just to get you into the swing of things. So we basically take Lagrangian and differentiate with respect to the derivative of Q, and that's going to give us Q dot. And then we differentiate with respect to the coordinate itself, and that's going to give us minus KQ minus lambda Q to the Q cubed. And then we take the derivative of this, right, and set it equal to this, right? And basically we get Q double dot equal to minus KQ. So that would be the simple harmonic oscillator thing, the spring constant K. And then we have an anharmonic term, Q cubed, like that, okay? Okay, now if you actually look back at the Lagrangian, it has what's called reflection symmetry, okay? Which means that the Lagrangian remains unchanged under letting Q go to minus Q, okay? So that's really easy to see. I mean, all of the Q's and Q derivatives are Q. So if you just let Q go to minus Q, basically Lagrangian goes back into itself. So under this transformation, which is discrete, basically the Lagrangian just goes back into itself. Right? And you might say, okay, well, what about the equation of motion? I mean, when I let Q go to minus Q, this changes, but so does this, and so does that, and then the minus sign cancels out. So basically, this system has a discrete symmetry. Okay, now. You can break the symmetry. You can break this symmetry explicitly by just adding another term on it. So basically, minus gamma, like this. Okay. So you guys see why that breaks the symmetry, right? Because basically, this term under this transformation or this discrete change, this would actually change sign. Right, all the rest of them would stay the same, but this would go into minus itself, so the Lagrangian would no longer go into itself. So basically, by adding that term by hand, right, you break the symmetry. And this is called explicit symmetry breaking. Okay, so now what I want to do is discuss. So this is basically explicit symmetry breaking. So now what I want to do is discuss spontaneous symmetry breaking. So often abbreviated as SSB. Okay, so let me do this by erasure. So explicit symmetry breaking is kind of dumb, right? It's just okay. Well, you can break the symmetry by putting stuff in by hand. But let's do something more clever. Okay. And we're going to change the spring constant. We're going to make it a wrong sign spring. So we're basically going to do that. Okay. So again, remember that Lagrangian is basically kinetic energy minus potential energy. So basically what that means is, and actually potential, let me write potential energy as V, right? So what that means is the potential energy now becomes minus 1/2 kq squared plus, right, lambda over 4 q to the 4th. Okay. So, well, I mean, what this is a wrong sign spring. So it's basically a spring. The further you get away from it, the more it pushes, which is weird, right? So, what does the potential look like? So, if we actually make a graph of this. So here's V and its function of Q. What this is going to look like is close to the origin. This term is going to dominate, right? So, I mean, for like very, very small q, so you might say, well, maybe it depends on k and lambda. Well, not really, because basically for very, very small q, because this is to the 4th and this is squared, this is going to dominate at lower q. And so let's take k, the spring constant, and lambda, the anharmonic piece, to be of the same order. And then what happens, you can definitely see at low q, you're going to get an upside down parabola, right? Which is basically, the opposite of a spring potential. Spring potential is a parabola like this, but because I've changed the sign, now basically it goes like this. But now as you go to large Q, of course, now the story reverses, and basically we have something that looks like this. So these are still stable points. Okay, these are all, well, no, these are all places where the derivative of the potential goes to 0, right? But this is an unstable location now. So it's gone from being stable when this was a minus sign. So when this is positive again, so you're going to have something that looks like that, okay? So now what happens is now the new ground state, even though the Lagrangian still respects that discrete symmetry, right? Changing the sign does nothing about breaking that symmetry, right? Because if I let q go to minus q, this term still stays the same, minus sign here notwithstanding, right? Does it matter? But the ground state is now shifted. And so now you've broken the symmetry spontaneously, right? The dynamics of the system has actually broken the symmetry for you, all right? So if you take a look at this, right? So I'll do some of the calculations. So basically, you want to find out where this is 0, where these minima are. And so then you get basically minus kq plus lambda qq. All right. So whether you put a 4 here or not, basically that's sort of conventional. And basically, they put the 4 and the 2 here just to make it so that you don't have any. So it's just k and lambda like this. And so again, you see that there are three places where this goes to 0. There's basically q equals 0, which is basically unstable, right? That's the old ground state. And now you also have basically q is equal to plus or minus the square root of k over lambda. And this is stable. Actually, these two are stable, right? Notice all of this is classical. These are all classical arguments. Okay. So, but what happens at the quantum level? So at the quantum level, in some sense, you, even though classically you've basically spontaneously broken the symmetry now, okay, if you look at the wave function that results from the ground state, the wave function actually still has the symmetry. So, I mean, if you look at this, the wave function that you'll get will still look, the ground state wave function will still look something like that, right? And so that still has the symmetry. So basically, you'll still have that the ground state wave function, when you say q, is actually equal to the ground state wave function at minus q. So in some sense, quantum mechanics doesn't taste the symmetry breaking, because the thing that's important, the wave function, still respects that symmetry. Okay, even though the Lagrangian that it comes from doesn't. But again, all these discussions here are purely classical, right? Now I'm going to make a transition to quantum field theory. And I'm going to keep my Lagrangian here. Well, let me pause you to drink a coffee and see if you guys have any questions. I mean, for you guys, this is probably, not so exciting, but. Okay. So now I want to go from want to make a transition from particles to fields. Okay, and there's a standard prescription for doing this. So basically, previously we had the coordinate as a function of time, right? Basically, to go to field theory, we replace that by a field, and in this case, I'm going to do a scalar field. That's a function of space-time coordinates. So basically, that's the generalization. So the Q gets replaced by the field, right? And this time dependence gets replaced by a space-time dependence. So if you haven't encountered relativistic notation before, let me just do a quick aside. Well, let me ask you guys, are you familiar with this relativistic notation? Right, so that basically x mu means the time part and then the spatial vector like that. Okay, so I've gone from time dependence to space-time dependence, and the action, which is the variation of the action is how you get your equations of motion in classical mechanics, and that's basically the time interval of the Lagrangian. Right. However, right, when you make this transition, what happens to the action is actually, well, it stays the same, except now you have to integrate over space-time coordinates. And so basically, let's say we have, let's say we're in a d-dimensional space-time. So basically the number of space-time coordinates is d minus 1. So for example, we live in a four-dimensional space-time, one dimension of time, three of space. So if we were talking about our universe, basically d is equal to 4. So basically this is an integration over 3 spatial dimensions, okay? And so, because here we generalize from time to space-time, the integration has to go from time to space-time. And because we're integrating over the spatial coordinates, the Lagrangian is actually replaced by a Lagrange density, right? So the idea is maybe I should do a double interval. One interval is for the spatial parts, one is for the time part, like that. But I mean, conventionally, people don't write that. They just write one integration, and it's understood that you're integrating over all the space-time coordinates, okay? But that's actually the new feature here, is that basically, to get the Lagrangian, you have to take the Lagrange density, and you have to integrate it over space, okay? So now let's see what happens to this under that sort of dictionary of translation. So we want to get a Lagrange density, and basically this first term is actually replaced by 1/2 basically d mu phi, which sometimes I'll write as basically, in kind of a lazy way, you can write like that. Okay, so this represents this term right here, right? So here I've taken a time derivative and then basically replaced it with a space-time derivative. And again, so that basically this is going to be 1 over c times the time derivative, and then the rest of it is going to be the gradient, like that. So with the lower index, yeah, I'm not going to worry about upper index and lower index, but I think basically with the lower index, it's a plus sign here. So anyway, so this is sort of a generalization of this kind of idea. So you have the space-time vector, And this is basically a space-time operator, which sort of corresponds to the gradient. And it's basically how you generalize the time derivative here, okay? Then we have minus the potential term. And actually what I'll do is I'll write minus V of phi, right? And so basically we're going to follow what we had here. And actually at first, let me go back and let me say, well, let's be reasonable and let's actually put a proper harmonic oscillator. So I'm going to change the sign. Remember, for Lagrangian, it's minus V, so I put a minus here. The potential is actually this. Okay. So if I do the translation here for potential, what am I going to write? I'm going to write basically that the potential is going to be plus 1/2 m squared phi squared, and then plus lambda over 4th e to the 4th, like so. Okay, so that's, and then all of this, of course, gets subtracted from that. All right. Okay, well, this piece right here seems to be just a direct translation from this using that dictionary, right? But here I've actually put m squared. Why didn't I stick with k? Well, terms like this are actually mass terms. So basically terms that have like phi squared in them, basically these kind of things are mass terms. And I'll show you why that is in shortly. But for now, just for 5 minutes or 3 minutes, just take my word for it, that terms like these, what they represent is the mass of this field, okay? So let's write down our Lagrangian that results from this. So basically, our Lagrangian is going to be, right? It's going to be that Lagrange density. And now I'm going to do something a little bit odd. I'm actually going to take part of this and put it with the potential, all right? So if I expand this out, let me actually expand this out. So this is actually going to be 1/2 times the time derivative squared minus 1/2 times spatial derivative squared, and then close brackets. Okay, so I'm expanding this out. So again, with this relativistic notation, and 0 means the time derivative, or actually time derivative 1 over c, and then basically the when this is I, right? When mu is equal to I, and basically that represents the spatial derivatives. Okay, and then the Lagrangian that we get from this is actually given by the spatial integral of that. And what I'm actually going to do is I'm actually going to pair this with that as part of the potential term. Okay. The reason for doing this is then it looks a little bit closer to here, because then this is a time derivative just like this, and so then you can pile that with that as a potential term. Okay. So anyway, then let me do that. Potential energy is going to be, so I'm extracting part of this, which is basically that. So the potential energy is actually going to be d minus 1 to the x, and then 1/2, and then plus squared plus lambda over 4 to the 4th, like that. So this is then my potential energy. This is actually potential energy density, and then volume integrating that gives potential energy. And notice I've left the minus sign behind. Left the minus sign, so there's a minus sign that should be in front of all of these when I stick it back in Lagrangian, but I've left that behind. Okay. Now, if you take a look at this, we want to minimize this. We want to find where the minimum is. Okay. And so basically, if you take a look at this term is positive definite. So, and basically what it represents is a spatial variation of the field. So if your field varies over spatial distances, then this will give you something non-zero. but it's positive definite. So the way you would want to minimize this is you want this to be not a function of space, right? So you want basically di phi to be 0, which means this doesn't depend on space at all, right? And so then basically this goes away, and then you're only left with this term, which then you want to minimize, okay? Well, if you minimize this, that gives you something fairly trivial. Now I'm trying to look what can I erase? So I don't want to, anyway, so the camera is only on this part of the board. So, and I can't really slide it up. So anyway, let me just erase all this stuff over here. So I think I'm done with this. Keep this. Okay. So basically we want to minimize that. Well, and actually, all right, let me do it real quick. So basically we have dv, d phi, and that's going to be m squared phi plus lambda 4 cubed, and we want that equal to 0. Okay, so great. Phi is equal to 0 is definitely a solution, right? And it looks like we have another solution, but actually we don't. And actually, there's no 4 here, so the lambda is gone. So let's say we solve this. So one of the solutions obviously is 0, but 0 in both of these means 0 here. If it's not 0, then we can divide by 0, right? And then we basically get m squared plus lambda phi squared is equal to 0. And then if we solve that, we get phi is equal to the square root of minus m squared lambda. Now, if m is a conventional mass, right? If it's a real mass, right? That gives us an imaginary, right? That's a no-no, because basically this is a real scalar field, right? And so this is not a solution, right? So so there's only one minimum here, only one acceptable minimum, which is this, which is, again, if you take a look at this term right here, and you plot v as a function of phi, what you'll get is you'll just get a very steep parabola. You'll get something that's steeper than a normal parabola because of the phi to the 4th term. So it'll just be very much more narrow. Okay. Now, let's do something provocative. Okay. Let's basically change the sign in here. And hold on. Did I want to? Let me. Okay. So I'm going to cut. Well, the provocative thing I'm going to do is I'm going to change the sign in here. But first off, what I want to do is do a side note and explain to you guys why I'm calling that a mass term. So this is a side note. Okay, now let's go back to basically a free scalar field of Lagrange density. So in other words, this is actually an interaction term, right? So basically this term represents an interaction of the scalar field with itself. And so my claim is that this is the mass term. And so what I want to do is I want to look at a free scalar field. And so that means I don't want any interaction. So I'm going to set lambda equal to 0, okay? And what I want to show you is by doing this, I'm going to end up with the Klein-Gordon equation, right? Which is essentially the relativistic Schrodinger equation, okay? So, let's begin. So basically, we still have the same kinetic term. We still have basically 1/2 and then we're going to have minus 1/2 m squared v squared, like so, okay? Now, let's derive the equations of motion for this. Remember how normally the equations of motion from Lagrangian are obtained in this way, right? So now, the thing that we do is basically take the Lagrange density and we differentiate it not with respect to Q, but with respect to phi, because phi replaces q, and not with respect to time derivative, but with respect to space-time derivative, with respect to that. Okay, and then instead of differentiating this with respect to time, we have to differentiate this with respect to the spatial coordinate. This is upstairs, which means downstairs, so this should be upstairs. And then that's going to be equal to the Lagrange density. Now, before we take the derivative with respect to q, but again, q goes over to phi, and so basically we take the derivative with respect to phi. So that's how our equations of motion work out. And again, I guess it's better if I write these side by side so you can see. So it's basically d dt of dl dq dot equals dl dt, right? So if you take a look at this and look at this, these are basically how you obtain the equations of motion from a field theory based on what it looks like from the particle point of view. Right? So this is sort of a direct translation. Okay, let's take a look at this. Well, this is the easy part to figure out. This, if I take a look at this, this is basically just going to be minus m squared phi, right? And this is going to be, okay, you have to juggle the indices a bit, but let me not worry too much about that. If you can raise and lower the indices, you take the derivative, there's two of these factors essentially, and so you're going to get basically d mu phi like that, okay? And then you can bring this term over here, and so then what you have is d mu operating on phi plus m squared phi is equal to 0. Okay. And then this is often written as box. The reason it's written as box is if you take a look at this, this is sort of a generalization of the Laplacian, and so this is D'Alembert. So basically what it is over c squared is t squared like this. That's essentially the wave equation. I might have a sign on here. Right, am I missing a sign? Damn it.
The sign might be opposite.
So I think you need this, you need that. Plus m squared phi is 0 plus m squared phi is 0. And basically, so I have this essential wave equation, this mass term, and this. This is the Klein-Gordon equation. The modulo, okay, there may be some sign issues here, but okay, so great. Where does this come from? What does it mean? Well, it's a wave equation. We know relativistically, things. The wave equation is a relativistic thing, but actually more. If you take a closer look at this, you can make the sort of identification that the energy is I h bar ddt. Again, the sign review off, and the momentum is this one. This one I'm a little bit more confident on is this, and so this connection. Actually, it's a connection. This connection you're probably more familiar with. That the momentum, right, in quantum mechanics becomes the following operator, okay? And the energy, now I'm wondering about the sign. So, but anyway, maybe the sign is correct.
Yeah,
is right? Okay. Anyway, so then if I take a look at this, if I put all this together, then this term right here is kind of like e squared. This is like minus p squared, right? And then so the m should be different because the m goes on the other side, and it's squared like that. So somewhere I've screwed up a sign, right?
Actually, I'm guessing that not everybody has seen this, and the whole thing with a mass is central to this, right? And getting it with the right sign might be really interesting. So it might be worthwhile just carrying over the calculation, assuming that phi is a plane wave.
Okay,
It's just cracking through to see that this is actually mass. So the phi, you can assume it's an amplitude that times e to the I kx minus omega t.
so e to the I k x
Minus omega t.
minus omega t.
And we know that k and omega are related to momentum and energy.
So basically, this is going to be e to the I p x h bar, and then basically minus I, and then basically this is going to be et over h bar,
Right.
like that. So
we can do the derivatives.
okay, so let's take a look at this. So this is what this is what I'm claiming I have, and then I'm saying, well, that is equal to this, and so basically what we do is we take this plane wave in here. So basically for a plane waves model free particles moving along, and so let's see what we get out of this. That's a good idea. So basically take two time derivatives here, and what we're going to pull down is we got a -1 over c squared, and then basically we get minus I e h bar all squared, right, to pull that down. And then I'm going to get basically plus I p h bar squared. And I'm saying I have a plus here, right? I have a plus m. So that may be wrong. But, and then all of this, so basically I've just carried out these operations, and then basically the field, this plane wave, this free particle that I'm doing, that's just along for the ride. Now if I do that, and then that should equal to 0. Now if I do this out, yeah, the sign on the m is wrong, because if I square this, I'm going to get basically e squared over c squared h bar squared, and it's going to be plus to have that. You know, maybe well, so maybe.
Yeah, so
Maybe I had the sign wrong here. So if I do that, then it works out. All right. So I had the sign wrong here. So basically, the D'Alembert is basically plus the second time derivative minus the spatial derivative. Anyway, so then what we have, so this is actually a plus. The momentum is actually going to be a minus then h bar squared, and then basically, and actually. There's a factor C that I'm neglecting somewhere along the line. There should be that's good. And then basically it's plus m squared equals 0. No, it's screwed up again. It's supposed to be minus because it's got to go to the other side. Anyway, so let me not try to hunt up. So actually homework for the students is like hunt up the correct sign. So what should come out of this is basically, this is the Klein-Gordon equation. And by looking at plane wave solutions like that, what you should get out.
I think.
What now?
No, I think you had the right signs.
I had the right sign?
Yeah.
Okay.
So,
Let me not try to dig through signs here, because okay. But and that's actually, it's a good exercise for you guys. It is. So aside from the fact that I screwed it up, it is actually a good exercise to run through the signs. And so basically, if you do either what Gerardo said, which is basically assume a plane wave, which represents a free particle, or basically you do the replacement that I had here, of course with the correct sign, this basically translates into e squared minus p squared c squared equals m squared c to the 4th. Right. So anyway, the point is, this is not some kind of mysterious thing, right? This Klein-Gordon equation. There's a very, very good reason why the Klein-Gordon equation describes a free scalar field, right? Because basically, it's essentially the same information as this, except this is for particles. This is the energy of the particle. This is the momentum of the particle. This is the mass of the particle. But basically, when we go over to waves or fields, right? Then we get this wave equation, right, which has solutions like this. So these are basic. This is a wave, so it's a field, a wave in a field, but it basically has these particle properties embedded in it. So again, this is this whole quantum mechanics thing of like particle wave and so forth. All right. Anyway, so so the whole point of this rather long and winding aside was just to convince you, maybe not very rigorously, that basically this term, right, represents the mass term. And actually the sign of it is kind of important, okay? But believe me, this is correct and basically corresponds to this. All right, now, so if we take a look at this potential right here, so again, we take a look at this, and if we look at the plus, so we take both of these to be positive. Well, what happens then? Let's find the minimum of that potential. Oh, that's where I left off on my aside. I said, okay, well, let's find the minimum of that. That's my potential. Let's find the minimum. So what we do is we say V d phi, remember phi is like the Q, we set that equal to 0, and then this becomes basically m squared phi plus lambda phi q. Okay, so we have the solution phi is equal to 0. That's going to be an unstable ground state, and we also have, we also have basically phi is equal to minus m squared over lambda square root. So basically, if you take this, set it equal to 0, one solution is phi is equal to 0. If the solution is non-zero, you can divide out by phi, and then you can find this as the solution. However, again, if m is positive, right, then this is negative, and that makes this imaginary, which is a no-no because it's a real scalar field. So, okay, we're done, right? So this is not a solution to that. So what do we do? Okay, well, we still want to follow the example from the point particles and basically break the symmetry dynamically. Well, let's do that. And so here's where the sign of this is actually important. We basically assume that there's a negative mass squared term, right? Now, and then you can make a graph. You can say v of phi, and then what happens is the potential goes from this when m squared is greater than 0 to this when m squared is less than 0. Okay. Now, this is very provocative because what does it mean when when you take m squared and you let it go negative? That actually that's tachyons, right? So basically, you're contemplating tachyons by doing this, all right? But the point is, at the end of the day, you're not going to get tachyons out of this because basically it's only tachyon if you choose to basically work here. That's no longer the ground state. You can see from the potential that basically the ground state is basically either here or here. Okay, so let's go ahead and change the sign. So I changed the sign here. So that's going to change the sign here, right? So basically now I'm considering basically m squared less than 0, right? And I'm putting the sign explicitly by hand, right? So I actually go, right? So then I still have phi is equal to 0 as a solution, but now that's an unstable, right, region. And then the other two solutions are actually plus minus the square root of m squared over lambda. So basically I have two new minima, right? So I've dynamically broken the symmetry because if you look at the Lagrangian, right, if you look at this Lagrangian right here, it has that discrete symmetry, but now in the guise of a field, right? Because I take phi and I let it go to minus phi, the Lagrange density remains invariant. So it still has that discrete symmetry. Okay. So what should we do? Right. So as it stands, right, we have tachyons in our model, right? That's no good. But that's only if we expand around the wrong region. So basically, we have tachyons and we expand here. That's obviously not the ground state, so we need to expand about here or here. So how do we do that? Oh, let me do one more thing. Let me say one more thing. Remember in quantum mechanics, I said the point particle case, right? When we were talking about Q and Q dot, and I wrote down basically the similar looking potential, except again, it was a potential for Q and as a function of Q, not phi, right? And I said, well, when you go to, that was all classical. When you go to quantum mechanics, right, the quantum mechanics somehow doesn't sense that symmetry rating. The ground state wave function still has the symmetry where you take Q, go to minus Q, okay? And another way you can think about that is in ordinary quantum mechanics, say you find yourself over here, there's always some probability to tunnel over here. So basically you can mix these two states in with one another, okay? Now, in this case, well, let me go back to ordinary quantum mechanics. So basically ordinary quantum mechanics, when I have V as a function of Q, then basically there's a barrier like this. And basically for the point particle case, you have basically V as a function of Q, you have Q over here. And basically what this difference right here is basically this barrier height. That's what that is. Basically, this right here is the value of the potential at, say, this point. And basically, this is the value of the potential here. And so this represents a barrier, right? And in quantum mechanics, if you find yourself over here, you can always tunnel through to that side, okay? However, things are a little bit more subtle in quantum field theory, because remember, the thing that replaces this is now this. So we actually, to get the potential, right, we have to integrate over space the potential density. So I'm actually, this is a little bit bad. I'm using V here for potential, but actually it's really potential density. So what I need to do, I need to get my potential, my actual potential for the field theory case, I need a volume integrate, which means integrate over this. And so basically, but then I still have, I still have a barrier, right? And now my barrier in this case is going to be basically the same kind of thing. Right? So basically it's the same kind of thing, right, as I have here. Again, so the V here is potential density, whereas the V in the point particle case is actually just the potential energy. Okay, so I have this, and then if you take a look at this, well, that's this potential barrier, right? So yeah, so you can actually tunnel through to the other side, right? And then just as in the ordinary point particle quantum mechanic case, you can sort of mix these two. Actually, not exactly, because these are actually constants. These are constants, so they actually can come outside, right? They can come outside your integration. And now you're going to integrate over space. And if you integrate over all space, this is basically infinite. This is some constant. This is infinite. So in field theory, there's in some sense an infinite barrier, or a barrier that is extensive in the sense that it grows with the volume of your space. So if you have an infinite space, that's an infinite potential barrier. And actually, even in quantum mechanics, if you have an infinite barrier, you're not going to tunnel through, right? And so that's a difference between the point particle case and this. And so basically the symmetry breaking is a little bit stronger in the field theory case than in the point particle case. Okay. So now, what should we do? Well, we're going to do the same thing we did before. We need to shift. We need to expand our Lagrange density around the correct vacuum. What we've been doing so far is basically pegging everything to here. We need to actually go to one or other of these locations. Okay, so let me do that. So we need to clear some space. Let me write down my Lagrange density again. It's going to be 1/2 phi it's gonna be plus 1/2 m squared v squared, again, the wrong sign, minus lambda over 4 to the 4th, like this. And then, as I said, we need to expand this thing around around this point or this one. Actually, so that's where the symmetry breaking occurs. You have to pick one of these, and basically it's 6 of one, half a dozen of the other. So pick one to expand around, and I'm going to pick this one. Okay, and so basically I'm going to define a new field called phi prime is equal to the old phi minus this. Right. So basically, I'm subtracting off this from this field, and so basically this is expanded around this point. If I were to expand around this point, then I would have a plus sign here, right? Again, I have a vacuum here, which is basically plus square root m squared over lambda, and over here it's minus square root m squared over lambda. And I have to choose, right? I have to break the symmetry, and I choose this, right? If you can go, so a homework exercise is, see how this works out. If you make the other choice and you take a plus sign here, which means you're expanding around this, you'll find basically the same structure. Okay, let's do this. So first off, this is okay, right? If I take this and I replace phi by phi prime plus the square root of m squared lambda, and then basically d mu, and then basically phi prime plus the square root of m squared lambda, right? What I'm doing is here I have phi, and so I'm taking this, I'm putting this over on the other side, I'm sticking it in, I'm taking the derivatives. Well, the thing is, when I basically work on this, these are constants, so the derivative term is going to kill them, and so this basically just reduces to 1/2 d mu phi prime, d mu phi prime. So this term is actually invariant. It's actually invariant under that shift. So it doesn't matter, okay? Now, this is a little bit more interesting. So basically, it's like minus 1/2 m squared and then phi squared plus lambda over 4, phi to the 4th. So what you do, again, is you put the phi in here. So it's basically minus 1/2 m squared, and then phi prime plus the square root of m squared lambda squared, and then plus lambda over 4, and then basically phi prime plus the square root of m squared over lambda to the 4th. Okay. So I'm not going to do. You can do this out. It's not too terrible, but in the interest of time, let me go ahead and say you expand these out, and then you see what things look like in terms of phi prime. If you do this, what's going to happen is the following. You're going to get a minus 1/4 m to the 4th lambda. This is a constant, right? Before in the non-symmetry breaking case, when you're starting here, you had 0 energy. Now, basically here, the vacuum actually has some energy, and that's what this represents. Then this you have to actually go through, right? You have to go through the algebra to check this. But what you find is actually plus m squared phi prime squared. Okay, there's some interplay between these two terms. You're going to get a phi squared term from here, and you definitely get a phi squared term from here. The phi squared term from here is negative, but this one that you get from here is positive enough that the overall mass is going to be positive. We fixed the tachyon problem. We no longer have tachyons because it has the correct sign. And then basically you get plus lambda to the 4th, phi prime to the 4th, plus lambda over square root of m squared lambda phi prime cubed. Okay, and basically notice this is the right sign. It has the right sign, right? Relative to this. Okay. Also, the mass though has changed. It's not a mass of m, but it's actually a mass of square root of 2 m. That's actually the mass of this new field. So the new field has actually a different mass. Because again, remember, when you grind through the Klein-Gordon equation, or you connect this with the Klein-Gordon equation, the factor of a half here is because you differentiate, you get a 2 here. If you don't have that, what that means is your mass is no longer m as it is here, but it's basically square root of 2m. So now you have a different mass than you started out with. Well, first of all, it's not tachyonic, and second of all, it's not m, but square root of 2m, right? And you still have a quartic term. So this term really hasn't changed. I mean, it's still the same. But now you actually have something new, another new thing, which is basically a cubic term here. So basically, you've added in a cubic term. So basically, by shifting things from here, the incorrect ground state or the incorrect vacuum to here, we now have actually a reasonable potential. Okay. All right. So let's. Okay. So this is basically spontaneous symmetry breaking of a discrete symmetry. There's no Goldstone boson here yet. To see a Goldstone boson, you have to break a continuous symmetry, and that's what I'm going to start next. Okay, but let me get a drink of coffee and see if you guys have questions. And Dan, smile. What's up?
Oh, or nothing, just that you're getting a drink of coffee.
Okay.
Use on the square root of 2, and that's
What? Oh, the square root of 2?
Yes.
Okay. Normally, right? This represents a mass term. So basically, having a term in the Lagrangian, right, like this, right? Basically, this leads to your equation having a mass m, right? Notice here, you don't have that factor of 2. So there's no factor of 2. So if you want to, so you basically have m squared, c squared like that. Okay. So then if you want to make a connection, basically you should take that. So this is kind of sloppy. You take this and put it over here, right? And maybe let me make this like a, you make this mass prime. So just something to differentiate the masses. Then if I want to compare these two, then I should take the square root. And so basically m prime is then the square root of 2 times m, like that. I mean, it's basically because the normal mass term for a real scalar field has this half factor. And after we grind through all this, the final thing does not, right? So the mass has been shifted by some amount. And the amount that is different by is the square root of 2 factor. But anyway, the point is the mass is different and it's real. It's actually a real mass. And again, we've broken, so there's no Goldstone boson here, right? So because we've broken a discrete symmetry. All right.
Actually, the point that you just made with the volume there is a really interesting to look at, because if the volume is finite, right, then the quantum system can tunnel from the left to the right, from the right to the left.
Yep.
So it can restore the symmetry.
Yeah.
But if the volume is infinite, it gets stuck on the other side and it cannot tunnel through.
Yeah.
And now you break the symmetry.
Yeah.
Right. So
yeah.
The infinite volume is crucial.
Exactly. Yeah. Exactly. So a lot of what I'm getting here is from Anthony Z's book. So let me just say, actually, there are 2 books, Ryder and Z's book. Z's book is like it's like beauty, right? It's like, but like it's really short on calculations. Right. Ryder is like in the trenches, like doing all the calculations and stuff like, which I like. Because I mean, I screwed up the mass, the sign of the master, right? So basically, but the 2 of them together are really good because basically Z gives you basically this grand overall view of quantity that's really beautiful, right? But I haven't decided yet if you need to basically go through the trenches with something like Ryder or Peschkin and Schroeder to really appreciate what Z has to say.
Oh, probably, right? Because Z is sort of like David Copperfield physics.
Yeah.
Right?
Yes. So the thing is, that's what I was thinking. If I didn't know a lot of stuff before, if I just read Z's book, I was like, right, that's coming out of nowhere, right? But it's if you do get to a certain level, Z's book is beautiful. So it's Anthony Z. It's called quantum field theory in a nutshell. which is garbage because it's like 600 pages long. That's not a nutshell.
And that argument with the volume is coming from Z? Or?
Coming from Z, yeah. I mean, the thing is, I think a lot of Z is a good expositor, but I don't know how actual original he is. I mean, the only thing I know from him that it was really his was the Julia Z monopole, right? Or no, it's a Julia Z dion, right? Mm-hmm. So, which was basically just a simple generalization of the Tufts-Polyakov monopole. Right. So it's like, I mean, there's being a good expositor and being a good scientist. And usually the two don't mix. Like sometimes they mix. I think like Feynman was good at explaining stuff, and he also was good at that. Like Dirac, like
Sidney Coleman, right?
Yes, Sidney Coleman, yeah.
He was good at both.
Yeah, he was. So anyway, so all right, let me start with, are you guys still okay? Because I'm going to start in on the continuous symmetry, which is the beginning of the actual Goldstone stuff. All right. So if you break a discrete symmetry like here, okay, no Goldstone bosons, but the groundwork this lays basically will allow us to very quickly get at Goldstone boson. So actually, well, it should be breaking of continuous symmetries. So the breaking should actually come first. But let's consider the following Lagrangian. So basically d mu phi. So now I'm going to actually consider a complex scalar field, okay? And I am going to put in a mass term, and I'm going to put in a fourth power or quartic interaction, right? And so I put the mass term in with the wrong sign, which is what I want to do, right? So okay. So notice this is again the potential energy density, and so it's kinetic minus potential, and so this actually has the wrong sign. This has the right sign, right? Because actually, when I go back, this is minus, and then this is plus. Now, okay, what happened to the 1/2 and 1/2 here? Okay, I've got you. Because basically, this is a complex scalar field, right? And there's a trick. You can write the complex scalar field as 1/2 times a real scalar field plus another real scalar field. So phi1 and phi2 are real scalar fields, and so this is a representation of the complex scalar field, right? I mean, this is just a generalization of the usual real and complex parts of a complex number, okay? Or real and imaginary parts of a complex number. So if I take this and I stick it in here, what am I going to get? So in terms of these guys, I mean, so again, this is something that's good to work out. I would get 1/2 d mu phi1 squared plus 1/2 d mu phi2 squared minus 1/2 m squared phi1 squared plus phi2 squared, and then basically, let's do plus now, and then minus lambda phi1 squared plus phi2 squared all squared. So like that. So basically now, what you see is this complex Lagrangian with this sort of transformation is really two real scalar fields. So one complex scalar field, not unsurprisingly, is actually equivalent to two real scalar fields, right? Because you see the kinetic energy term here. So again, I'm using a shorthand. So this should really be something like this with phi1, and the same thing here, right? So these are, mu phi1, mu phi1. Phi1 and phi2 are real scalar fields. This is a complex scalar field. Okay, and so basically this basically is the same thing as this. So and then you have your mass terms, and then you have interaction terms here. Okay, so Tori, you oh. All right. So this Lagrangian, so let's go back to this form though. I'm going to come back to this form. This actually has a continuous symmetry called U1, unitary group of dimension 1. U1, and actually it has a global. All right. What does that mean? That means that if I take my phi and I let it go to e to the I lambda phi like this, the Lagrange density remains the same, right? This is a constant. That's why it's global. This is the same constant everywhere in space-time, everywhere in space-time. And then you can immediately see these terms right here. Basically, if I take phi and phi star, I'm going to have e to the I lambda and e to the minus I lambda. They cancel. Then the same thing here, okay? Then here, since lambda is a constant, it doesn't get touched by the derivative, so it comes through, and you've got a e to the I lambda, e to the I minus I lambda, and they go together and cancel each other. So this Lagrange density is invariant under this continuous symmetry. And why is it continuous? Well, you can take lambda to be anything as you want. You can take it to be like really, really tiny, really, really large, anything in between. So it's a continuous variable, right? So whereas before we were taking the field and we were saying phi goes to minus phi, right? Which, by the way, this also still satisfies that. This is just a larger symmetry because basically this is that if you take lambda to be equal to pi, right? But now lambda can be anything in between, right? By the way, so this is another thing. This is actually related to, or is actually connected with rotations in a plane. So it's actually connected with special orthogonal two-dimensional group, right? I don't know if you've seen this in your classical mechanics classes, but basically this kind of representation can be used to represent rotating stuff in a plane. Okay, so if you want to have a physical picture, it represents like rotations in a plane. Okay, and I mean, if you do this out, this is e to so e to I lambda is like cosine lambda plus I sine lambda, and then if you look at two-dimensional rotations, you can write it as a matrix like cosine lambda minus sine lambda plus sine lambda cosine lambda, right? So let me not take a side detour to show that that's true, but basically, if you want to have a physical picture of what this U1 symmetry is, it's essentially rotations in a plane. But be careful. This is not rotations in space-time. This is rotations of a field. So this is an analogy, right? This is in field space, right? This is no coordinate here. There's no coordinate here at all, right? It's a field. So you just think of this as rotations in field space. Okay. All right. So now, with that set up, again, if we take a look at this potential, and actually let's go back to the minus sign. So let's suppose our potential had the correct sign, right? So it had plus sign here, and then plus sign for the lambda. Then if you make a plot of this potential as a function of the scalar field. Now notice I have to put the scalar field in a plane. Before, when I had one real scalar field, I just had a line and then my potential went that way. But now the scalar field basically is in this plane right here. And so what I have is this sort of paraboloid like that, right? So if I have the right sign here, then this is the kind of potential that I get as a function of phi, which is actually phi is now in the plane. And basically I have one real vacuum, which is right there. So that's my only vacuum. Okay. So however, if I do the following, if I give it the wrong sign, right, which is again allowing tachyons, this is going to be a little bit harder to draw. So now I'm going to have this. It's also going to come out this way. It's going to come back this way. And so what I'm going to have is, and this red line right here at the bottom, that's the bottom of this Mexican hat or wine bottle. So this is the famous Mexican hat or wine bottle potential, right? Depending on what you prefer, right? So, but anyway, so the minima now is here, and it's as compared to the previous case, there's a continuous set of vacua that are basically here that are connected. Before, remember, we had that just one scalar field, and the vacuum was either here or here. Now we have sort of a whole continuum like that, okay? And so again, by choosing this sign right here, even though this Lagrange density still satisfies this symmetry, the vacuum state now no longer does, okay? And so let's find out where the minima are. So I'm going to take this. I'm going to take this one right here, and I'm going to say dv dphi is equal to minus m squared phi star plus 2 lambda phi star and then phi star phi. Okay. You can also, so again, in this case, you should also take the derivative of the potential with respect to phi star, but the result that you get isn't going to be any different. So, and here I should be careful. This is actually with respect to not phi1 or phi2, but with respect to phi, the real scalar field. Right. So if I take the derivative of that right there, with respect to phi, you can see I'm going to get this. Yeah. Okay. So then, and we set that equal to 0, right? And one solution is basically phi is equal to 0. So phi is equal to 0 is then here at the top of this mountain right here, this local maxima. So that's unstable. So, but what about the local minima? So if you can solve this, and you can find out that basically there is another solution, which is basically an m squared over 2 lambda. So basically just solving this, right? You divide out the phi star and just solve for this. And then this is basically the magnitude of that complex scalar field. Okay. So notice this only fixes the magnitude of the complex scalar field. It says it's equal to that. So basically the distance from here to here, that's that distance. And what it's saying is any place along here, right, that has that same magnitude will be a vacuum. Okay. So now what we have to do, and let me do one other thing to make things easy. Let me define this to be A. So this is what's called my vacuum expectation value. So it's called, right? 0 is usually the vacuum expectation value that people are familiar with. But in these systems, the vacuum actually has a non-zero value, which is given by this. And I'm going to write it as A just to make the subsequent calculation simpler. All right. And I'm almost done. So you guys still have like 5 more minutes. You guys still okay. So we have to shift. We have to shift it. We have to shift our field to the correct vacuum, just as in the previous case. So first, let me remind you that for a complex field, right, you can always write things as an amplitude, right, and as a phase, right? And so these are our 2 degrees of freedom. Now, there's another way of doing this, and I'll basically mention this at the end. You can also write it as basically, you can also write this down as, which we already did before, 1 over the square root of 2, phi 1 plus I phi 2. So in other words, you can write this complex scalar field in a polar representation or a Cartesian representation. But notice in both cases, there are 2 degrees of freedom, either phi 1 and phi 2, or the amplitude and the phase, okay? Now, let's take this and see what happens when we stick it in here. Well, no, first of all, we actually have to do something. We have to, well, this is what we would do. We would take this and stick it in here if we didn't have a non-zero vacuum. But again, we have to expand around the new vacuum, right? So what we're going to do, we're going to define our field phi, and it's going to be basically expanded about this new point, but shifted by a, and then e to the I theta x. Okay. So the first thing to notice is that basically if I take this and I stick it into here, right, then basically what I'm going to get so d mu phi and then d mu phi star is going to be equal to d mu rho primed times d mu rho primed, but then, and that's when the derivative operator acts on this guy right here, okay? And then notice the phase factor cancels out, right? But then I'm going to get basically plus rho prime plus a squared. Remember, a is the vacuum expectation value of basically d mu theta, d mu theta, like that. Okay. So this is a standard kinetic energy term for this. When I square this out, I'm going to get phi prime squared. I'm going to get a cross term. I'm going to get a squared. So the a squared term times this up to some constant is a standard kinetic energy term for the phase factor. So we have 2 fields, phi primed and theta, that basically have sort of standard kinetic energy terms. Now, what are these terms? The phi prime squared on this, that's an interaction term between the fields, right? It's kind of a weird one. And then there's a cross term, which is basically phi prime times this, which is also another interaction term, right? So, but what now, the interesting thing is what happens with the potential. So we're going to take this and we're going to stick it in here, okay? So if we do that, what's going to happen is the following. We get v to the phi is going to be equal to minus m squared phi star phi minus lambda phi star phi squared. Actually, that's the beauty of this expansion right here, is actually you don't have to worry about this field at all, right? Because it just completely drops out. The only thing that you get from this is you get basically a minus m squared rho prime plus a squared from here minus, oh wait, this should be plus. That should be plus because I chose the wrong, I took the wrong tachyon sign. And basically this is going to be rho prime plus a to the 4th. Okay. Again, I'm not going to, the calculation here is very similar to what we did before for the single scalar field with the discrete change. You can expand this out, and what you get is the following. You get a minus m squared, you get a lambda rho prime to the 4th, you get a plus 4a lambda rho prime cubed, you get a minus lambda a to the 4th, and then you get a plus 4 lambda a squared rho prime squared. Okay, that's what you get by expanding this out. Okay, so we have two fields now. We have basically rho prime and we have theta. Both have kinetic energy terms, right? The kinetic energy term for theta comes from this term squared, right? We have interaction terms. We have a lambda phi rho prime to the fourth. That's actually very similar to what, the phi to the fourth here. Actually, we generated a new cubic term. That's different. We never didn't have a cubic term. Now we have a cubic term. We have another constant term. Again, this is all similar to the one-dimensional real scalar field. And we have a mass term for phi prime. Notice phi prime has a mass term. This is phi prime squared. So this basically represents the mass of that field. And actually, if you want to write it down, it's basically rho prime squared is going to have a mass of 4 lambda a squared. And then if you put in what a is, that's going to be equal to 2m squared, right? So again, here you can see the square root of 2 mass thing before, explained a little bit better than I did previously. But anyway, the point is we've developed a mass term for phi prime. But notice there is no mass term for theta. That's the Goldstone boson. Okay, so basically we start off in a system, right, where if we had the correct mass sign, we would have two fields. You have two fields, say phi1 and phi2, or rho and theta, that both had masses, right? But then after we go through the symmetry breaking here, right, what ends up happening is the rho prime field, when we expand about the correct vacuum, the rho prime field does have a mass term, but then the other field lacks a mass term. That's the Goldstone boson. Okay, and let me just say one thing, because this is a little bit more transparent. You can basically do, instead of, okay, so let me pause here and see if you guys have any questions about this. All right, so let me just say, instead of, instead of doing this kind of representation of the field, you can also do this. So, but you don't want to do this. You want to shift it to the real vacuum. So basically you do this. You do 1 over the square root of 2, and then basically phi1 plus I phi2. Okay. So exercise. Do everything that I did for this representation with this, grinding it through here, and what you'll get at the end is the following. You'll get Lagrange density is like 1/2 1 squared plus 1/2 mu phi2 squared. You'll get a -2 lambda a squared phi1 squared. You get a minus square root of 2 lambda phi1 squared plus phi2 squared. And then you'll get a minus lambda over 4 phi1 squared plus phi2 squared all squared, like that. But that's what you get. After all the kind of calculations that I did with this, if instead of starting with this, you start with this Cartesian representation, but shift it to take into account the proper vacuum, right? You grind through everything. Take my word for it, you get this. And here, the advantage of this is that the calculations are somewhat quicker. This takes a little bit longer to work out, but then at the end of the day, it's a little bit more transparent what you have. And here in the Cartesian representation, you can clearly see, aha, I've got two kinetic terms for two real scalar fields with the correct factor of 1/2, right? Versus here, not. Okay. Then you have various interaction terms. This should be phi1. So these are just interactions between the fields. These are interactions between the fields. This is the mass term, but only for phi1, right? Not for phi2. Phi2 doesn't have a mass term. It is massless. Phi2 is the Goldstone boson, right? Now, so if you guys, well, that's actually the end of my lecture. That's good. So if you found that useful, then what I was going to do next time is show how this plays out for a higher symmetry, like SO3, and I'll have to explain maybe what SO3 symmetry is, just rotations in 3 dimensions, and then show how symmetry breaking works out there, and then show in that case you get actually 2 Goldstone bosons, right? And then there's this whole theorem about like, depending on how many symmetries you break. So you start with some original symmetry, and then you break the symmetry down to some level. And then the number of Goldstone bosons depends on the difference between the generators of the symmetry you started with and what you ended with, right? And so that's what I was going to do next time, and then maybe prove the Goldstone theorem, and then maybe talk about Landau-Ginzburg theory, which is actually what Dan was interested in, I think, because that's actually the application of all this stuff to condensed matter physics, right? And by the way, so the phi here, right, for particle physics, this is the Higgs field, right? Well, not this one, but eventually it's the Higgs field. For condensed matter physicists, these are things like the wave function or the order parameter for the Cooper pairs, right? So, and Cooper pairs are electrons that are bound together via phonon vibrations, and basically, so electrons are spin half particles, but if you bind them together, then you have a boson, which is what we have here. But the reason we got onto this is Dan had some questions over Christmas break, and actually I realized that condensed matter symmetry breaking is much richer than particle physics symmetry breaking. You know, and so Dan had questions like, why only a scalar field? Can't you do some other things? I'm like, no, you can't. It's like, well, it says in this book that magnons are Goldstone bosons, and they do have spin limit. I'm like, read. Oh yeah, you're right. So anyway, and the tori, not to put you on the spot, but if I would be interested to learn a little bit more about the condensed matter side of things, because Dan's questions really made me realize that while I may understand very well, or think I understand very well, how symmetry breaking plays out in particle physics, there's a lot of things that are in condensed matter physics that I don't know.
I can definitely protect some lectures. It's very vast, so we will need to chat a bit to decide the path.
Okay, yeah, so I'd be happy to chat with you. Yeah. So, and if you don't want to do it, that's fine. And so also an April colloquium is good if you want to.
Sure.
Yeah. Okay. All right. Well, so hopefully you guys found that useful, Dan, especially. So, and if you guys want, we can do this again next Friday, because I think I have enough material for maybe 1 or 2 more lectures.